Lecture 23 covers sections 7.5 through 7.7. At the end of today's lecture, you should be able to analyze the behavior of an inductor as a function of time. That is, you should be able to determine the voltage established across the inductor based upon the time rate of change of current running through it. And you should be able to construct an expression for the behavior of inductors connected in series and parallel configurations. To begin, we have to describe what an inductor is. An inductor is shown in the figure to the left, where a voltage potential exists across insulated wire that is wrapped around a magnetic core. Within this insulated wire, you have some type of magnetic material, and as current runs through this wire, it induces a magnetic field. This magnetic field is where energy is stored. Now, the strength of this magnetic field is dependent upon N, the number of turns of wire. And the inductance of our material, which stores our magnetic field, has a variable L in units of henries. Now, the voltage potential established across an inductor is a function of both the inductance L and the current running through it I. That is, our voltage potential V of t is equal to L times the time rate of change of current running through our inductor. That is, if we do not have any time rate of change of current, we do not establish a voltage potential across our inductor. The current flowing through the inductor is simply solved by re-expressing our expression for a voltage across the inductor. That is, I of t is equal to 1 part inductance times the integral of negative infinity to t of v of tau d tau. If we say I of t naught is the current initially running through our inductor from negative infinity to time t is equal to 0, we can say our current running through our inductor is equal to I of t naught plus 1 per L, the integral of 0 to t v of tau d tau. Now, I of t must be continuous since v of t is bounded. This is an important consideration to make when analyzing systems. What's unique is if we compare constitutive equations of a capacitor and inductor, they take a very similar form. The current entering a capacitor is equal to the capacitance times the time rate of change of the voltage potential established across. Similarly, the voltage potential established across an inductor is equal to inductance times the time rate of change of current running through it. These two equations take a very similar form. And when we couple these with Ohm's law, we can have a complete description of passive and active devices covered within this course. And these devices form the bases for RLC circuits.